Welcome to 9.1 Sampling Distributions and Confidence Intervals for Slope. So we are going to briefly introduce the sampling distribution for linear regression models, and then we're going to talk about how you can create confidence intervals to talk about the true slope of the population. So one thing I want to quickly go over, if we were to take many least squares regression lines, so linear regressions of the same size from a sample population, we're going to create a sampling distribution because every time you pull a new population, you're going to get a new sample regression. So the goal and what you're generally trying to figure out is what is the true population regression line? What is the real data? Now, it's nearly impossible because, again, a census is the only way that works, and most of the time, not really easy to do. So, what we do instead is we take samples, many of them, and we build up a sampling distribution. Now, our sampling distribution typically centers around our mean. So, starting at the point where what shape do I want? Well, ideally, you want it to be approximately normal, and we'll talk about the condition that is required for it to be approximately normal in just a second. But remember, if it's approximately normal, it's going to center around my mean, and we call that beta. Mu of b is equal to beta, and it's going to go out by my standard deviations. Now, I know this formula looks a little complicated. Trust me, it actually kind of is. So we are not going to really focus on using the formula. This is one of those things where we rely heavily on the calculator. But again, I like you to see it just in case you wanted to try it by hand. This formula is made up of the standard deviation of residuals. And what we're going to do is we're going to use S, which our calculator is going to generate for us, and then our standard deviation of X, our explanatory variable, a similar calculation, and then sample size. Again, it gets a little bit complicated. That's why we're going to move in the direction of the calculator for these types of problems. So, confidence intervals. We have done these before, and we have done panic. Anytime we have encountered a confidence interval, we've gone through the steps of panic. Define the parameter, check your assumptions and conditions, name the method, calculate the interval, conclude in context. I kind of put these a little bit out of order because there's some things that we're familiar with, some things that change a little bit for linear regression models. So our parameter does change. It's not mu, it's not p, it is beta, and it's going to be the true population slope between explanatory variable x and response variable y. Our method is going to be a linear regression t interval. Yes, you have to name the method in order to get credit, especially because we are going to be relying heavily on our calculator. Our conclusion looks pretty similar. We can be blank percent confident that the interval from blank to blank captures the true slope between x and y, something we've been familiar with ever since we started confidence intervals. Where things get a little bit different and a little complicated is with the assumptions and conditions. We are very used to checking three things: randomness, 10% condition, and some form of normality. Now that is here. We do have those pieces. We do have randomness. We do have is it normal, and we do have the 10% condition in these assumptions and conditions for linear regression. Now we also have a little bit more. There's two new ones. We have is it linear, and we're going to see the scatter plot and see if it's linear. And does it have equal standard deviations? Basically, we're going to check the residual plot and make sure it has a random pattern. Everything else is kind of similar to what we did before. With the normal, we're going to check histogram of residuals to verify that it looks approximately normal, and randomness and independence will come in the same way it has before. The easiest way to remember all of the conditions required for a slope confidence interval is liner, L-I-N-E-R. Now, for the actual calculation, it looks pretty similar to what we've been doing. We have a point estimate plus or minus. The second half is still going to be called our margin of error. It is a critical value. t star times a standard error. So B is going to be our point estimate. That's going to be the slope from our sample. T star, we're going to use inverse T to find this. And then we have our standard error. Now, the general formula does include sigmas because it's talking about the population. However, again, we don't know what the true population differences are. We only know the differences of our sample. So we call this the standard error of B, since both of these are going to come from sample data. And the way we actually write it out in our formula, standard error of B is the standard error of the residuals over the standard error of x times square root of n minus 1. One other quick note, when we're doing inverse t, it's going to ask us for area and degree of freedom. For this case, we are going to use degree of freedom n minus 2. Okay, now we're going to go through a really long example, and then we're going to talk about how you might actually see it on the AP exam. So example 1, the data in the following table gives 15 states and what their average teacher salary is and how much they spend per pupil expenditure. Construct and interpret a 95% confidence interval for the slope of the population regression line. And what type of relationship does this interval suggest? Explain. So we have a couple of things to do. We are going to go through the steps of panic. So first I'm going to start off by defining my parameter, pretty easy. I'm going to say beta is the true population slope between average teacher salary X and per pupil expenditure Y. Now, my assumptions and conditions are where it gets very, very long. I'm going to have to go through all 5 of Liner. The first one is to check if they are linear. So I'm going to do that in my calculator. I'm going to put all of my data from L1 or from X into L1, all of my data from Y into L2, which I have already done. So I'm going to go ahead and pull that up for us to see. So stat edit. I have all of my data in L1. I have some extra crazy data going on over here in L3 and L4. We're going to ignore it. L1 and L2. So I'm going to go to second y equals plot 1. Going to turn it on. And I'm going to make sure scatter plot is selected. I want it to plot L1 for my x's and L2 for my y's. And then I'm going to hit zoom 9. And I get my scatter plot. And for the most part, it looks pretty linear. It's not perfect, but it's linear. So I'm going to, and what you would do is you would sketch a picture of your linear scatter plot. So I would go in, I would draw my x-axis, I would draw my y-axis, and I would do my best to kind of model where the dots are if that is something that they ask you to do. Now, typically what they'll do is provide you with a scatter plot, so you may not have to do this part on your own. And since we have a moderate positive linear relationship, we're going to say this condition is satisfied. The next condition is independent. So that's my 10% condition. Now we run into a little bit of issue here because I know there's only 50 states and my sample size is 15. If I were to multiply that by 10, I get 150, and 50 is definitely not bigger than 150. So it's going to violate the 10% condition, but I'm going to continue on because on the AP exam, you will never stop for conditions. Make a little note in your conclusion, continue on. So N is going to be my normal model. So I want to look at a histogram of the residuals to make sure that that is normal. So this is something we haven't necessarily done before, but we've done the parts of it prior to putting them together today. So the first thing you have to do in order to work with residuals is you have to actually calculate your linear regression line. So I'm going to go to stat calc, going to go down to number 8. I'm going to say my X list is L1, my Y list is L2. Now you want to be careful because we're coming out of probability. You may have this say L2. We don't want that. Delete it, leave it blank. Biggest mistake I believe people will make going into Unit 9. Calculate, and I get my linear regression model. Now that I've done this, my calculator has something to compare my Y values to because it has the line, the model. So now I'm going to go to second, Y equals. I'm going to go back to plot 1. Not a big deal. I'm going to select histogram. And I'm only going to have one option for XList. I'm going to go down to second stat, this little list option, second stat, and you should see resid, number 7. Now, if you don't see this, it's because you did not run the linear regression model. Go back, stat calc 8. So I'm going to do 7, and then I'm going to do zoom 9 again, and I'm going to get a histogram. Now, if I look at this, it's not perfect, but I am seeing a normal model start to occur. I do have a potential outlier. I'm going to make note of it. But again, if you are encountering this on the AP exam, it's not something where you're going to stop. I know it seems kind of silly that we're checking all these conditions and continuing on, but it's just the nature of the game. We keep going. So again, if I were you, I would just sketch my XY axis and do my best to kind of simulate where my histogram bars are. I always make a little note, looks approximately normal with one potential outlier. It seems to be New Jersey is our outlier. It's a little bit higher than everybody else. So we've got LIN. E is the next one, and that's going to be our equal standard deviations. So that means I want to actually just look at the residual plot. So I'm going to go back to my calculator, lots of calculator work on this one. I'm going to go to second y equals. I already have my residuals calculated, so I don't need to do that again, but I do need to go back to scatter plot. I'm going to make x list L1, and I'm going to make y list second stat resid. So resid. So L1 and residuals. And then do zoom 9. And when we generally look at our residual plots, we want to make sure that we're seeing no curve forming. No pattern really. You want to have randomness scattered everywhere. So again, I would sketch a XY axis, well, an X residual axis in this case, kind of simulate where your dots are. No strong pattern, no skew in the residual plot. So we're going to say, like our previous one, this one is also met. Run into another issue, randomness. It's not stated that it's random. So again, not the biggest deal in terms of answering an FRQ question, but it does make us a little weary of our results that we get at the very end because we do have 2 conditions that failed for this. So now we're going to go on. We finally finished our conditions. Going to go to linear regression T interval. Going to go into my formula. So with this formula, there's a couple of things I need to find. I need to find B, I need to find T star, and I need to find the standard error. I said this is a long problem. It's because it's a long problem. We will make this much easier on ourselves in just a second. So B is coming from that linear regression model, from that stat calc 8 on L1 and L2. Remember, you do not want frequency for this. B comes from the second line, 0.428. It's the slope of our sample. T star is coming from our fact that we want a 95% confidence interval. Remember, if I have 95 in the middle, that means I have 2.5 in each tail. So inverse T, second bars, inverse T asks us for 2 things, area and degree of freedom. So I always take the positive one. You could very easily take the negative one. I do 95 plus 2.5, which gives me 0.975. And my degree of freedom is my sample size minus 2, and that's noted in our formula. So 15 minus 2 is 13. So I get my T star, 2.1604. Now the standard error is where I'm going to tell you not to freak out, because again, a lot of this we're doing in the calculator. You will never have to calculate this by hand. So I'm going to go over it, but I'm not going to go into too much detail on it. So we're taking our standard deviation of the residuals, which you can do in your calculator by doing 1-bar stats on the residual values, and our standard deviation of x values, which you can do, again, with 1-bar stats on the x values, times square root of n minus 1 gives us approximately 0.1199. We're going to talk about how your calculator does this for you in just a second. For now, we're just going to trust that Ms. Contreras' math is accurate and the standard error of our slope is 0.1199. I use all 3 of those things, Put them together into my formula. I get the negative version is my lower bound, positive version is my upper, and I conclude. We can be 95% confident that the interval from 0.1618 to 0.6798 captures the true slope between average teacher salary and per pupil expenditure. This suggests a positive relationship between the two. So, this confidence interval is capturing what the true population slope would be for my entire population, not just my sample. My sample is the 0.4208 I used in my calculation. I did make a note, however, not all conditions for inference were met, so results may be invalid just because we did not pass the independence and randomness condition. Okay, that problem was a lot, and I'm here to tell you they will never ask you to do all of those things. I promise. More than likely, when you encounter a slope regression inference problem, they're going to tell you the conditions are verified. They are not going to make you go through the steps of liner that may show up as a multiple choice question where they ask you about them, but they will never make you verify them by typing in all of that data into your calculator and doing all of that on your own. Another thing to be thankful for, a lot of the time for problems like these, they give you something we call a computer output. So we call this a mini tab output, and we have a couple of things given to us here. So let's go ahead and talk about what is actually shown. I know it's a lot of information, but there's things you need, there's things you don't. First, let's talk about the things you don't need. This constant line, the standard error of the coefficient, the t and the p, you're never going to use them. Cross them out as soon as you see it, ignore it entirely. Another thing that you will never use is the r squared adjusted. Never going to use it. Don't even worry about it. The things that are important to you is you're going to have something that either says constant, I believe sometimes it says like y-intercept. It is going to be basically your y-intercept. So this is like our a value. And then you're going to have something that's indicating what's being plugged into your equation. This is our b, our slope. So this is like our y-intercept, and this is like our slope. Two very, very important things because it's where you build your linear regression from. We then have our standard error. Remember that thing I told you would never have to calculate on your own? Here it is. They gave it to you. Most likely, that's what's going to happen. T is going to be our critical value in terms of a hypothesis test. And p-value we're familiar with because it is a probability. Now, this is something we're going to get into tomorrow, or the next class period, but it is based on a null of beta is equal to 0, alternative of beta is not equal to 0. We'll talk about hypothesis tests next week. Now, two other things that you might need. S is going to be our standard deviation of residuals, and R squared is our coefficient of determination. Now, if you are asked for the R value, the correlation coefficient, all you have to do is take the square root of R squared to get R. Pretty straightforward. So this is just breaking down what is given to you in a computer output. So let's go ahead and put it to use. A study attempted to establish a linear relationship between IQ score and musical aptitude. The following table is a partial printout of the regression analysis and is based on a sample of 20 individuals. So I have my computer output, and they are asking, what is the 99% confidence interval for the slope of the regression line? Does this suggest a linear relationship? Assume all conditions have been checked and met. Again, most likely that's what they're going to tell you. So we are going to be doing a confidence interval. Before I get started, I know I need b plus or minus t star times standard error of b. So I'm going to pull what I need from my problem. So I know that b is my slope. So you're always going to look for what value is being plugged into my equation. So this is my b. This is my b value. And then I need standard error of b, which is here. Standard error of b and b. Everything else, Not really important for the sake of this problem. So let's go ahead and get started. Beta is the true population slope between IQ and musical aptitude. Assumptions and conditions have been verified. The name of the test is a linear regression T interval. Now we are going to go through the process of calculating the confidence interval given this computer regression. Really, the only thing I need is T star, and that is something we've done before. So I have B plus or minus T star, standard error of B. I know T star is going to be based on a 99% confidence interval, so I'm going to enter in an area of 99.5 and a degree of freedom of 18 because 20 minus 2 is 18. Gives me 2.8784, and that's just me doing it in the calculator in second bars, inverse T. And then I have my two values from my computer output, plug them into my formula, and I get a confidence interval of 0.1428 to 0.8422. Last step is to conclude in context. We can be 99% confident that the interval from 0.1428 and 0.8422 captures the true slope between IQ and musical aptitude. Much, much quicker than the long process we did in example 1. Now, before we move on, we did have one additional question. Does this suggest a linear relationship? Well, if I went ahead and looked at my confidence interval, again, remember, it's really, really important how we relate it to 0. Because this interval does not contain 0, this interval does suggest a linear relationship. And that's based on the whole idea that our null would be beta equals 0, and our alternative will be beta not equal 0. And we'll talk a little bit about that when we get to hypothesis testing. Hopefully that last problem made you feel a little bit better about linear regression T intervals. Now, I don't want you to worry if you do encounter a problem and they don't give you a computer output. We do have a calculator function that allows us to do this test pretty quickly and pretty easily. So stat test G linreg T ent is going to create a confidence interval for linear regressions. L1 will be our X list, L2 will be our Y list. Again, coming out of probability, be very careful with frequency. We want it to be 1 in this case. Make sure it doesn't say anything crazy like L2 or L1 or L3. Confidence level is generally indicated in the question. Most typically, it's 0.95. And if for some reason you want to see your linear regression line graphed, we can store it by writing Y1 in this blank. Most of the time, we'll just leave it empty because we really don't have to graph the line once we found it. So example 3, a random sample of 10 high school students produced the following results for number of hours of television watched per week and GPA. Determine the least squares regression line and give a 95% confidence interval estimate for the true slope. And again, like most likely will happen, assume all assumptions and conditions have been checked and met. So first, let's define our parameter. True population slope between TB hours X and GPA Y. All assumptions and conditions are met. We have verified them. N, we are doing a linear regression T interval. Now, for the I part, we are going to go to our calculator. So I'm going to open mine up to show you. I have my data in L1 and L2. I'm going to go over to stat, over to tests, and I want to go to G, linreg T int. Going to hit enter. It says L1, it says L2. Frequency I'm going to leave at 1. My confidence level for this question is not 0.95. It is, oh yes, it is 0.95. And I'm going to leave this regression line blank, and I'm going to calculate. So I get my confidence interval of negative 0.0887 to negative 0.0554. I get my slope. It tells me degree of freedoms. It tells me my standard error of the residuals, my y-intercept, and it even gives you r squared and r. So basically this is the computer output that you get in those little mini tab windows. So, like anything we do with our calculator, it's good to write everything down just to make sure that you get full credit. It's not required that you do the r and the r squared. Typically, I leave that off, so I get my confidence interval. Now, it does ask to give the least squares regression line. We have the y-intercept, we have the slope, so I just put this into a linear regression formula. Remember, you want to include the variables, so I put y is GPA with a little hat, because remember, y is the predicted value, and I put IQ in parentheses for my x. Now to interpret. We can be 95% confident the interval from negative 0.0887 to negative 0.0554 captures the true slope between TV hours and GPA.